Welcome back. This is Chapter 9, Confidence Intervals. So confidence intervals are something that we can use to try to explain, okay, there's a high likelihood that the thing that I'm looking for is inside of this little interval. So let's say I'm looking for 26 things sold, or what's the probability that I'm going to have 26? Well, if I have an interval from like, say, 20 to 30, then 26 is included in there. Does that make sense? And it's a very high likelihood that 26 will be included in there. Another way of thinking about confidence intervals is that if this is your confidence interval, then it's 90% or 95% or whatever percent likely that you'll randomly pick a number between 20 and 30 in whatever experiment we're doing. I don't know if that helped, but let's look at the examples and maybe that will. So we got 355 junior college students surveyed and 125 said that they had previously owned a motorcycle. Okay, so that's what I care about. Find a point estimate. So point estimate, we use p-hat. And by that's the hat. That's the way they call it when I was in college. So p-hat is going to be the number that you want, 125, over the total, 355. It's really like that. That's probability. That's the way it was back in Chapter 5. Nice. So really just 125 divided by 355 is 0.352. I don't know how many decimal places they want. Oh, 3 decimal places. 352. Boop, 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 boop. Yeah, I left the multiple choice questions on these. Sometimes you need a little help. Maybe that helped. Okay. Number 2. That's all they wanted. They just want the point estimate. Nothing about confidence intervals. They just wanted to get you into it. All right, number 2 asks, if you know that 88% is the level of confidence, then what this is saying is that it's 1 minus alpha times 100 is going to give you 88. So this is what I mean by 1 minus alpha times 100% confidence interval in the formulas. See, 1 minus alpha times 100%, that's what 95% ends up being. So we just have to figure out, what is this number? Well, we could divide by 100, and we get 1 minus alpha is 0.88. And then we could subtract this from 1, or we could subtract 1 and divide by negative, however you want to do it. 1 minus 0.88. And that is 0.12. And that's your alpha that they want. Now, they didn't ask what is the alpha. They said, what is the z alpha over 2? So what they're telling you here is this, that if your alpha is 0.12, we're going to divide it by 2, and they want the z-score that goes with that answer, 0.06. So alpha is 0.12 divided by 2 is 0.06. So we're going to look for this area in the normal chart. Still using these things, so it's very handy dandy to have them. 0.06 is a small number, so I'm going to look in these negatives. Looking for 0.06. Anybody seen 0.06? Eyes on 0.06. Oh, 0.0606 is pretty close, and 0.0594 is equally as close. So negative 1.555 it should be your z-score. If you wanted to round it, you could say negative 1.56 or negative 1.55. I wonder which one they say. 1.555. They want the 1.555. Now, here's the thing. With this, the z-score is a negative number because the area is so small, but that's because it's over here on the left side of the normal curve. But it is also positive 1.555 because we're talking about the alpha over here. So 88% confidence interval is talking about 88% over here. 88% confidence interval. Let me draw this normal curve. Told you I'm bad at it. Is saying that in between we have 88%. 0.88. So on the outsides here and here, that adds up to 12%. That's what I did when I said find the alpha. That's what's in the tails. So if I want to find one of these scores, I would divide that by 2, and that would be 0.06. And then I would find the z-score that goes with that, and that's a negative. But the positive one over here also goes with 0.06. Does that make sense? I'm trying to explain why. You don't need to know why, but you do need to know why this is positive. Because once you find your z-score, we're just going to change it to positive. All right. Number 3. For the purposes of confidence intervals, we want positive z-scores. So for number 3, it tells us a whole bunch of stuff. So first of all, let's just break down what's going on. We had a Florida newspaper talking about what teenagers want to discuss with their parents, which I don't believe these numbers at all. Teenagers don't want to discuss anything with their parents, probably. But that's, that might be because their parents have been pretty strict or, pretty repressive about what they're allowed to talk about. So I have a feeling that some of the cool parents out there who have teenagers, they probably do talk to them. I wouldn't know. I have a 5-year-old. Okay. So it says 46% want to talk about financial institution, 30%. These in percentage are based on a sampling of 5. So n equal to 540 is the first number I really want to write down. Those other percentages are for 3 different things, and I don't know what I want to deal with. Okay. Estimate the proportion of all teenagers who want more family discussions about school. So let's go to the percentage for school. That is 37%. Right? So in this case, my P is 0.37. All right? That's what I'm dealing with. The other 2%, I don't care. Not what I'm asking about. All right, and then it says use a 98% confidence level. So we're estimating the proportion of all teenagers. So here's 0.37. 0.37 is how I found it. 98% confidence interval means that my alpha, instead of going through this whole process of dividing by 100 and then subtracting it from 1, I'm just going to say, okay, what's 100 minus 98? It's 2, and that's a percentage, and then I go 2 places over, and that's 0.02. Okay? So subtract this from 100, and then move the decimal 2 places to the left. And that's your alpha. So my alpha is 0.02. Okay. Things that I need to know. So with a confidence interval is always p hat plus or minus the error. And that's the error is found by finding your z alpha over 2. See, that's why I made you do it. And then multiplying it by the square root of your p hat times 1 minus p hat all over n. So that's the formula that's in your formula sheet right here. That's what your confidence interval should look like, and that's what E is actually equal to, the margin of error, with a proportion, or a point estimate. That's what we're dealing with, point estimates. Okay, so I got to find Z alpha over 2. So that means alpha over 2 is 0.01, and that means Z alpha over 2 is equal to, I got to look at the chart for 0.01, small numbers, so I'm going to look on this one. 0.01, 0.01, 0.01, where are you? 0.0099 is pretty close. I'm going to go with that one. Negative 2.33. So negative 2.33. Sorry, I ran out of room. Okay, so that goes here. My p hat is 0.37. My z alpha is negative 2.33, or positive 2. Remember what I said? Positive. It's because of this plus minus here. It's including it, so I don't need this negative anymore. All right. square root 0.37 times 1 minus 0.37, which is 0.63, right? And that's divided by 540, which is my n, right? Okay, so I got some calculation to do. Let's see, 0.37 times 0.63 equals, and then divided by 540. Okay. And I need the square root of that number. Let's try this a different way. Square root, parentheses, 0.37 times 0.63 divided by 540. Oops. 540, close parentheses. And that is 0.020776589. We're going to multiply that number times 2.33. So equals, and then times 2.33. That gives me 0.37 plus or minus my error, which in this case they said they want their error to be to the nearest thousandth. That's 3 decimal places again. So I get 0.048. 0.37 plus or minus 0.048 is the error. Okay, that's how I find a confidence interval. So yeah, so the formula looks a little daunting, but it's just plug in these numbers. P hat's 0.37, that's 37%. And then alpha comes from the 98%. You know, subtract from 100, move the decimal. And then you divide it by 2. And then you find this number in the chart to see what z-score goes with it. Don't use the negative, just put it in there as positive, and then do a little calculation on your calculator. If you're having a hard time with your calculator, you get, maybe find this number and round like to 0.0208, and then multiply times 2.33. I don't know. If you got one of those nice TI calculators, then you don't need to do that. Just put it all in on one line. You guys are so spoiled. All right, number 4. Why won't you focus? There you go. So here we go. A national lobby's successful fight against gun control legislation is reflecting the will of a minority of Americans. All right, so first of all, when I read this problem, I was like, oh, they're going to think I'm politically biased and try to push my politics on you, in which case I want to kid and say, yeah, I do. But you know what? I don't really care about guns, honestly. I don't think we should have... You know what? It doesn't matter what I think. It doesn't matter what I think. I have a lot of strong opinions that you don't need to hear. So N is 4,000. Somebody sampled 4,000 citizens. And it got 22. So the point estimate is 2250 out of 4,000 agreed that we should have gun control legislation. And if we found that decimal by dividing, that's how we find a point estimate. This is like from number 1. We get 2250 divided by 4,000. We get 0.5625. So about 56% of those surveyed believe we should have gun control legislation. That's over half. That's interesting. So let's look at how we can describe this as a 98% confidence interval. What we're trying to say is, let's find an interval of numbers where this point estimate is 98% of the time going to happen. Does that make sense? So like, I'm very confident, 98% is very confident that 56% of Americans think we should have gun control legislation. So we want to find our margin of error, and that is my z alpha over 2 times the square root of p hat times 1 minus p hat all over n. Okay, this margin of error helps me understand that this sample is not exactly the whole population, but it is really close to it within a certain amount. So my Z alpha, and that's because our population is normally distributed for the most part, especially about the way people think and do things. It's normally distributed. It's almost always, every time. All right, so I need my alpha. This is 98%. So again, that's alpha is 2%, move the decimal, 0.02. Just like number 3. All right. So my alpha over 2 is 0.01. And that means my Z alpha over 2 is the exact same Z alpha over 2 as the last problem, which was 2.33. All right, so 2.33 times square root of 0.5625. And then the other one minus that would be 0.4375. And that's all over 4,000. Okay, now I'm going to do a little calculating. Delete square root parentheses 0.5625 times 0.4375 divided by 4,000 gives me 0.0078 and some change. And I'm going to multiply that times 2.33, and that's going to be equal to, so they want a confidence interval, right? So the p hat plus or minus e is going to be 0.5625 plus or minus, I'm going to use 10,000, so that's 4 decimal places. This is 0.0183 when I round it. There we go. And I'm going to check that answer. Number 4 is D. And it looks good. I rounded it to 0.183. They had 0.0182. That's okay. It's really, really, really close. Okay. So that's confidence intervals, babies. Now, a researcher wants to estimate the proportion of the adult population that has sleep deprivation. So how large of a sample is needed in order to be 99% confident that the sample proportion will not differ by more than 5%? So let's talk about what numbers they gave me. They gave me 99% confidence. So this is a 99% confidence interval, and that means that my alpha, 100 minus 99 is 1, move the decimal, and it's 0.01. Okay, that's one thing they gave me. All right, and then they said they don't want to differ by more than 5%. So 5% is the error. So E is 0.05. We don't want percents when we do calculations. So they want N. What is N? Wait a minute. Sample size has a formula. P hat, 1 minus P hat, and then the Z alpha over 2 divided by E squared. So I need to find my Z alpha over 2. So this would be the Z of 0.005. That's 0.01 divided by 2, 0.005. All right, let's go to the chart. It's a very small number, so I'm going to go to this one. Come on, focus. There we go. I want 0.005. Ooh, right here, right in between these two, actually. So it's negative 2.575. 2.575. 2.575. Focus. All right. Okay, and the reason why I have 2.575 is because it was right in between, and that's why I added this little 5 right here. Now, you could just have left it off and have 2.57 or 2.58, and you would have found the answer pretty close to the answer. And since it's multiple choice, that's kind of why I left it multiple choice. So you can find the answer choice that's pretty close to what you picked. Okay. So I've got z alpha over 2. My sample size is p hat times 1 minus p hat times z over e squared. So when I'm plugging this stuff in, I got my p hat. What is my p hat? That's the point estimate. So what is my point estimate? Well, a researcher at a major clinic wishes to estimate the proportion of the adult population that has sleep deprivation. So if they don't give you a point estimate, so no given p hat means we're going to use p hat is equal to 0.5, because it's kind of arbitrary what we're dealing with as far as the point estimate. And if we're not given one, we don't know one, then we're just going to assume half, and we're going to go with that. So if we plug in 0.5 and then 1 minus 0.5, which is also 0.5, and then the z alpha over 2 is 2.575, and the e is 0.05, but we're going to square that. Don't forget to square this part first and then multiply these two. That's the order of operations. Remember that jink? All right, so let's say clear. Parentheses, 2.575 divided by 0.05, close parentheses, and then square it. All right. I get 2,652.25. And that kind of makes sense. But we're going to multiply that. Oops. Is it equal? We're going to multiply that by 0.5 times 0.5. And we're going to get 663.06. And when we're doing these sort of things, we got to get a sample size that's going to do it for us. And so going over is going to do it for us, but going under is not quite. So that any decimal is going to round it up to the next whole number. So that's why the answer in this question is D, 664. So if you're not given p hat, it means p hat's 0.5. We have to arbitrarily say that. Okay? All right. I don't know if that was in the notes, but if it's not in the notes, aren't you glad you watched this all the way to this 23rd minute? Number 6, we have the same kind of deal. So we have a 90% confidence interval. And that means that my alpha is going to be, let's see, 100 minus 90 is 10. And I move decimal place, it's 0.10. Instead of 0.01, it's 0.10. And so remember, it's alpha z alpha over 2. So this is going to be 0.05. That's 0.1 divided by 2. And 0.05, going to the chart. Let's find it. 0.05, 0.05. That's 0.05. 0.005. 0.05 is right here in between these two. 1.645. 1.645. Okay, focus. There we go. 1.645. That's the z-score. And again, like I said, you can just say 1.64 or 1.65. They'll both work okay. All right, and then we're given the error. It wants to be no more than 3%. So the error is 3%, which is 0.03. And then it wants to estimate the proportion of United States voters who favor abolishing the Electoral College, which I am too in favor of. And that's not so political. I mean, it is political if you get into why I care about that, but if you don't care about why, that's not political. I really don't like the Electoral College for reasons. How large of a sample is needed in order to be 90% confident that the proportion won't differ? So again, they don't give us proportion. So we're going to say proportion is 0.5 again. So our n is equal to 0.5 times 0.5 times 1.645, our z-score, divided by e, which is 0.03, and we're going to square that first. Okay, yep. Parentheses, 1.645 divided by 0.03, close parentheses, raise it to the second. 3006.69. We're going to multiply that times 0.5 times another 0.5, and we get 751.67, which rounds up to 752. So our sample size needs to be 752 in order to be 90% confident that the error won't be more than 3%. Okay. All right. That was number 6. Number 7. A pollster. Oh my God, this one's long. Number 7, a pollster wishes to estimate the number of left-handed scientists. Okay, so we got 95% confident interval. That means that my alpha is 100 minus 95 is 5, so that's 0.05. That means my z alpha over 2, which is 0.05 divided by 2 is 0.025, is, go into the chart. Now I'm looking for 0.025. 0.025, do you see it? Yeah, no, it's 0.0025. Don't do that. Okay. 0.025. There he is. Right on the money. I love those. Negative 1.96. So 1.96. Remember, I don't need the negative for these. Okie dokie. What else they give us for number 7? They don't want to be true. They don't want to differ from the true proportion by more than 6%. So the error is 6%, 0.06. And the previous study indicates that the proportion is 8%. So they have a point estimate. 8% is 0.08. So in this case, we're not using 0.5. They gave us one. So our sample size is going to be 0.08 times 1 minus that, which is 0.92. And then times 1.96, the z-score, over 0.06, the error, squared. All right, calculator. Delete. So we get 1.96, oops, parentheses, 1.96 divided by 0.06, close parentheses, squared, is 1,067.1. And then we're going to multiply that guy times 0.08 times 0.92. And we get 78.5, which rounds to 79. Rounds up. Always round up. So we just need 79 people in this study in order to be 95% confident that the error won't be more than 6%. Okay. Oh, I'm still using this paper. What am I doing? Oh, God. Zoop. Number 8. All right, now we switch over to 9.2. All of that was 9.1. And this is 9.2. We talk about student's t-score. And I'm not talking about some student came up with a probability distribution. No, it was a guy whose last name was Student. What? Yeah. So it's student's apostrophe S. It's this guy's t-distribution. In case you were wondering where the word came from. It was some dude's last name. All right. So when it comes to t-distribution, degrees of freedom, no matter what, is always n minus 1. No matter what. It's a definition thing. And then for the student's t-distribution, a lot of things are very equivalent to the normal distribution. For instance, if you have a large sample, t and z are very close to each other, very close. And the t-distribution depends upon the numbers of degrees of freedom. And it's symmetric, just like the normal distribution. The thing that isn't right is the mean of 1. So A is the correct answer there, because the mean is actually 0 for student's t-distribution, just like normal. They said it's 1. That's not right. Okay. Now, I want to construct a 95% confidence interval for the population mean. Now, the reason why we have this is so that we can construct a confidence interval for the mean. And so if we're talking about trying to find a confidence interval for the proportion mean, that means we have a sample. That sample has a sample mean, x bar, and it has a sample standard deviation, s. Right? Okay. So this is sample, this was earlier, sample mean, and this is sample standard deviation. Okay, so before we were dealing with the confidence intervals using a z-score, we had proportions that we were dealing with. Here we're trying to estimate the mean, so we use the student's t-distribution. So 95% confidence interval means that my alpha is 0.05. Okay? Now, when we find this one, we have to find a t of alpha over 2, in this case 0.025. But a t-distribution depends upon the degrees of freedom. So my n minus 1, my degrees of freedom, n minus 1, depends on the sample size. In number 10, our sample size is 20 part-time workers. So our degrees of freedom is 19. So if I want to find the student t distribution, I wonder if this, I have somebody else's stats book. Maybe they got a good t-distribution chart. F chi-squares distribution t. Yeah. This is nice. Okay, so it's on the wrong page, but that's okay. I don't know what yours looks like, but it should look like something like this. So here, I don't know, just depends on what you're given. But degrees of freedom are along the left side, and the level of significance for a two-tailed test is what we're looking for here, not a one-tailed test. So for a two-tailed test, we want the level of significance to be 0.05. 0.05, we want to go down to 19 degrees of freedom, and that is 2.093. 2.093. Now, I kind of want to look up a t-distribution on the internet for those of you who don't have the book. So let's look up t. I'll even put in students t-distribution table. And the first, let me look at images. Okay, I kind of like this one. Let's open this up. Open image in new tab. Oh, that's not very big. All right, well, here I'll show you. So I found this one. And this is a student's t-distribution where we talk about two-tailed tests. Focus. Okay. So here they are dealing with alpha of over 2. So a two-tailed confidence interval, they tell you if it's 95%, that's my finger, it's a big fat finger, okay. If it's 95%, then your alpha would be 0.025 because it's alpha over 2. I'm sorry, two-tail, 0.05. And it'll do the point that. So in this case, when we're talking about alpha over 2, 95% confidence interval, two-tail alpha is 0.05. So a two-tail alpha, 0.05, and we go down to 19, and we get 2, are we at 95%? 2.093. And that's what I had in that other chart. So yeah. So this is a good chart. If you see it in your Google Images, I'd pull that up. Make sure you look under the two-tail alpha for 0.05 if it's 95% confidence. Look at the two-tail confidence level, 95%. That's the column you want. Okay. Back to this, though. Ooh, don't fall. All right. So they want you to construct a confidence interval around the mean. So several things I know is that the degrees of freedom is 19, 95% confidence interval gives me this t-score, and that the formula I'm going to use is this one, x bar plus or minus t-score times s over the square root of n. Okay? So I'll write it again. X bar plus or minus t alpha over 2 times s over the square root of n. So let's see, what do they give me? We find the mean x bar is $3,120. And a standard deviation, so s, is 677. And my n is 20. So plugging all that in, I get x bar is 3,120 plus or minus t-score, which is 2.093, times s, which is 677, over the square root of 20. All right, now I'm going to do a little calculating. So let's see, 677 divided by, parentheses, square root of 20, close parentheses. Okay, that's 151.38. And then I'm going to multiply that by 2.093. And I get 3120 plus or minus, and I'm only just working with this stuff right here. 3120 stays there. That's the mean. And then it's plus or minus 316.84. So that is a confidence interval for this problem, 95% confidence interval for this problem. And so that's not how they have it as the answer choices, though. They actually want you to add this number to this and subtract this number to this to get the two numbers in an ordered pair. So if I said 3120 minus 316.84, I would get, let's see, let's clear that. 3120 minus 316.84. That would be 2803.16. And then if I said 3120 plus 316.84, I could probably do that in my head. That's 3436.84. Okay. And so they went around it to the whole numbers, and so it's 2803 and 3437. So that's the answer that you're going to deal with. 2803, 3437. That's the confidence interval they want. Y'all didn't see that. Okay, there it is. Okie dokie. Now, which number is that? Let's do number 11. Number 11. So we only got two more, guys. Number 11 says construct a 90% confidence interval. So 90% CI means that your alpha is 0.1. Because remember, 100 minus 90 is 10, then move the decimal. So that means that we wanted a T of alpha over 2, which is 0.05. But if we're using that T distribution